Our differential equation here is the quantity of x plus 2 times y double prime plus xy prime minus y is equal to 0. And we can see that x equals 0 does not zero out the coefficient on the y double prime term. And so we have a power series solution, actually two of them, centered around the ordinary point x equals 0. As before, we're going to start writing down y equals the sum as n goes from 0 to infinity, c sub n x to the n, and then differentiate a couple of times. Remember, when we differentiate, we're using the power rule, so we end up with terms that look like n cn x to the n minus 1 and n times n minus 1 c sub n x to the n minus 2 for y prime and y double prime, respectively. And every time we differentiate a power series that has a general term x to the n, the index increases by 1. And remember that that happens because we lose a constant term when we differentiate. I'm emphasizing that now because things are going to be different in the next set of videos. Don't worry about that right now. For now, what we have is a binomial x plus 2 times y double prime. The way we're going to handle that is distribute the y double prime to x and then to 2. That's going to look like this. The sum as n goes from 2 to infinity of n times n minus 1 c sub n x to the n minus 1, because we're supplementing the x to the n plus 2 with one factor of x. So the exponent increases by 1. Plus, the sum as n goes from 2 to infinity of 2 n times n minus 1 c sub n x to the n minus 2. So the y double prime gets distributed, leaving us two terms. For xy prime, we have the sum as n goes from 1 to infinity of n cn x to the n, because again, x to the n minus 1 times x is going to give us x to the n. Minus y, there's nothing interesting happening here. It's just minus the sum as n goes from 0 to infinity of c sub n x to the n, and then the whole thing equals 0. As before, we're first going to make the exponents match, and then we're going to make the indices match. I'd like you at this point to go ahead and do that. Make the exponents match, make the indices match, and then write down the recurrence relation if you can get that far. Then come back and we'll compare notes. So I've made all the exponents match x to the k, and for the first term, first sigma expression, we have k times k plus 1 c sub k plus 1. For the second one, 2 times k plus 2 k plus 1 c sub k plus 2. And for the third and the fourth, the only change was that n became k, so those are unchanged. So I'd say if you need to, pause it here and then see that you match me, and then we'll move on to the indices. For the indices, for the second sigma expression, I wrote down the k equals 0 term is 4c2. For the fourth sigma expression, I wrote down the k equals 0 term, which is negative c sub 0. Everything left is going to have a starting index at k equals 1. We have x to the k in all the terms, so I meant to factor that out. And then inside of the brackets multiplied by x to the k is our k times k plus 1 c sub k plus 1, k times k plus 2 k plus 1 c sub k plus 2, and then c sub k can be factored out of k minus 1 from the xy prime and the negative y terms. From here we can write down a couple of equations. Number 1, c sub 2 is equal to 1/4 c sub 0 by setting the constant terms equal to 0. And then all the coefficients add up to 0. So we've got k times k plus 1 c sub k plus 1 plus 2k plus 2 k plus 1 c sub k plus 2 plus the quantity of k minus 1 c sub k equals 0. I'll write down in a moment that that has a starting value of k equals 1. At this point, what we do is we solve for the constant that has the largest subscript. That's going to look like c sub k plus 2 is equal to negative k over 2 times the quantity of k plus 2 c sub k plus 1, because for those terms, the k plus 1 divides out, minus k minus 1 over 2 times k plus 2, k plus 1 times c sub k. And here I'll write down k starts at 1, 2, 3, etc. That equation, together with the information about k's starting value, is the recurrence relation. Using that recurrence relation and the fact that C2 equals 1/4 C sub 0, I'd like for you to crank out terms for k equals 1, k equals 2, and k equals 3. See what you get, and then come back. When k equals 1, I get C sub 3 is equal to 1/6 C2 minus 0, and since C2 is 1/4 C naught, C3 is negative 1/24 C naught. For k equals 2, we have C4 is 1/4 C3 minus 1/12 C2, but C3 is in terms of C0, C2 is in terms of C0, and as it turns out, we get 196 C sub 0 minus 196 C sub 0 equals 0. C5 is negative 3/10 C4, but C4 is 0, minus 1/20 C3, but C3 is expressed in terms of C sub 0. So when k equals 3, we get C sub 5 is equal to 1 over 480 C sub 0. Now that we have all the constants straightened out, what I'd like you to do is write down what you think are 2 power series solutions. I didn't write anything down because I wanted you to see how this would unfold. If you want to, skip to the end. Remember, our power series solutions have the form y equals c naught plus c1x plus c2x squared, and so on. Here we have y equals c sub 0 we get for free, plus c sub 1x we get for free. C sub 2 we saw was equal to 1/4 C sub 0. So our next term is 1/2 C sub 0 x squared. And I know it's x squared because that was associated with our C sub 2 term. Next, we have our C sub 3 term, so I know it's going to give me an x cubed. And the coefficient is negative 1/24 C sub 0. For C4, our term was 0, so we don't have one of those. For C sub 5, we have plus 1 over 480 C sub 0, and then again, it's our x to the 5th term, because it was C sub 5. And then here we have plus ... there. Divvying things up the way we did before, I see several terms that have C sub 0, and I see one term that has a C sub 1. What that means for us is that y1 is equal to, if we were to factor out the C sub 0 and then pull apart the superposition solution, y sub 1 is equal to 1 plus x squared minus 1 over 24 x cubed plus 1 over 480 x to the 5th. I'll generally just ask for 3 terms, but since we had those, I wrote them down. y2 is simply x. It's the solution that we have that's multiplied by C sub 1. I thought we were expecting 2 power series solutions. Technically, x is a power series. It just has one term. And if we look back at our original differential equation, we saw that it was x plus 2 y double prime plus xy prime minus y is equal to 0. If we consider the solution y equals x, then this negative y is negative x, y double prime is 0, and x times the derivative of x is x. So we end up with x minus x equals 0, and that means it's the solution. So even though that may be unexpected, here are the 2 solutions to the differential equation.